Hey folks, good morning, good afternoon, good evening, whatever time zone you are in. Let's talk about vector search and vector search in the modern databases. First, few words about myself. I am a founder at Percona, Altinity, FerriDB, and Karoot. I'm the long-time open source database enthusiast and really the advocate of open source technology. I'm also speaker at a variety of conference, advisor, and investor in number of projects. So why vector search? Well, if you look at the modern world, the things have evolved a lot through the traditional keyword search, right? Because not all the objects are text those days. Think about Netflix, for example, which may provide you some movies, right, where you're looking for some particular content, or if you would be looking for something like a trail running shoes, right? All of those tasks can be much better handled with an understanding of a context rather than just looking to match keyword descriptions, because different people may use different word for that. But it also goes beyond that, as we'll talk about it. The vector search underpowers a lot of functions in a modern AI landscape those days. So let's start with an important reveal, if you like. What is the status of a vector search in the databases? And we can see a very interesting situation. The databases, of course, existed for many, many decades, while vector search is something which is relatively new, right? The first technologies or first database introduced that back in 2019, which is just 5 years ago, right? And some databases just introduced it in just 1 or 2 years ago. Some, like PlanetScale, just recently announced their vector search offering. What you can also see their unfortunate example here, which is the MySQL, which is still very popular open source database, which is now owned by Oracle. And so far, we have not released any vector search in the open source edition, and it's only existing in MySQL HeatWave, which is cloud bound. Now, what is interesting is what even traditional databases have been very focused on a vector search those days. Like, for example, you can see Elastic advertises itself as the most downloaded vector database, right? You don't even use the vector search here, the word, right, which is, some other used. And why is that? Well, this is because the vector search underpowers many AI applications. And probably you know what AI, especially generative AI, is very big, and a lot of companies are either building the new applications of AI or really looking how to use AI for their internal works. Another example would be Enterprise DB, which is the PostgreSQL-focused company, right, which has been in business for a very long time. And recently they have been rebranded itself as their AI database, right? Which is, again, because we have sort of an AI, the gold rush, and many database companies are doing what we know works very well. In this case, is just to sell the shovels. Now, before we go into some specific examples of the databases, let's talk a little bit about vectors, right? And if you are wondering what does this picture have to do with vectors, well, This is just like a fitting illustration about how AI thinks. I've asked the Mindjourney, generative AI app, to create me some vector pictures, and that is what it's came up with. So why, when we talk about AI, we talk about the vectors and vector search, right? Of course, for many people, AI is this kind of wonderful thing, like a self-driving cars, maybe, image recognition, or, ChatGPT, which can answer a lot of, questions, or help to generate, text, code, and whatever, right? But if you look at internals of how all those AI and ML systems works, they are using a lot of math, in particular, the linear algebra. And this linear algebra deals a lot with the matrices and vectors, right? So then we have to deal with some real world objects. Typically would have something like an image, converted to its vector representation. Then there is a lot of maps that goes out depending on the task, right? Maybe you have to classify what that image is, right? Or maybe, compare what similar images are, and so on and so forth, right? And on output, again, we get the vectors which can be converted back to the objects you want to deal with. Now, for a lot of tasks, what you have to do is we have to compare vectors. And that is what is often referred as a vector similarity, right? Which is, well, basically some sort of distance between them. Now, the good way to think about the vector similarity, right? You don't have to be like, think in particular as a, distance of the 2 points on the map, also to think about the colors, right? If you would want to mathematically figure out how similar are two different colors, well, you may remember what the colors are typically represented by RGB, right? Or some other, vector representation, but let's use this for simplicity. And you can basically present two colors by two of those vector representations and do some sort of similarity math between them to find out what colors are similar or different. Now, what is interesting in this case is there are different ways how you can compute that distance, right? Those could be cosine similarity, right, which is defined as an angle between the vectors, right, which actually may be useful with colors, right? If you want to figure out, let's say, something between a very, dark or almost black orange and a very, bright orange, well, if you want to treat that as pretty much the same color, then their intensity doesn't matter, right? Just direction does. In this case, cosine similarity works very well. Right now, if you want to treat more of a kind of like a distance or direction and intensity at the same time, right? Then their Euclidean distance or dot product would work the best. And really depending on specific use cases, right? One or another vector similarity may work better or not, right? For example, in a text search, often cosine similarity is very good, because if you are thinking about like a, text talking about a car, or text has a lot of car, well, that's, still text about car. But if you think about something like a, image recognition, when somebody has a big nose or really big nose, well, that's very likely to be a different person, because, well, in this case, size matters. Now, if you look specifically about OpenAI, right, one of the very popular models recommendations, they suggest using cosine similarity. And why? Well, because in their case, they normalize all the vectors, right, in the embeddings, right, to in the length, and in this case, those are basically very similar. Now, in search applications, we are often dealing with two kinds of vectors. One is sparse vectors. So what is the sparse vector? Well, the sparse vector is a vector which has pretty high dimensionality, but most of the values are pretty much zeros, right? They have no data, right? And then that's why we keep it sparse. In text processing, that often would be the vector which basically has the dimension for all words, known words in the alphabet, right? And then there would be either 1 if a word is present and 0 if it doesn't, right? Or maybe the relative frequency of a word, right, will correspond to every word which are met in a document. Obviously, most words will contain the small fraction of the words which are present in a dictionary, so most of those would be zeros, right? And that is a very common representation which is used for full text search engines, right? For like algorithms for last 50 years. Now, if you look at the vector search solutions, a lot of those use the dense vectors, right? The dense vectors, they really have a valuable data in every dimension, right? So there is no, or well, maybe some, but not a lot of zeros in this case. And those are produced not with some trivial text processing, but through embedding generation, right? And embedding is something what their AI model can generate from you, right? It can generate vectors from images, from sounds, from scents, and so on. So, and if a model is good, then that will correspond to the meaning what that object has, right? So, for example, if you want to compare the cat and a dog, right? If you use kind of classical text processing technologies, right? Those would be actually quite different, right? There is a, the measure of a distance between words, right? For example, as defined of a number of different characters, and we can see all the characters are different, right? There in cat and a car, it's just one character difference. But if you would look at embeddings, then cat and dog probably would be much close than a cat and a car, right? And I think that is a very important difference to understand. Now, if you ever wondered, okay, but how do embeddings look like? There was this interesting project done, which computers relatively low dimensionality embeddings based on, the model trained on Wikipedia content for those different words, right? And in reality, of course, you would have embeddings which have much longer dimensionality, right? So you would typically see hundreds of thousands of dimensions in an embedding, but in this case, it was specifically relatively small, so it's hard to illustrate. So easy to illustrate, right? And what is interesting in this case, right, is what there is kind of, we can look at that at least, and there is, you can maybe judge, well, some similarity, right? You can see there's like a certain areas are similar between, all the females, right? And you can see king and queen have some other similarities, right? And so on, and so on and so forth, right? And the order is kind of the most different from everything, but you cannot really reason very specifically what different things mean. And I think that is important to understand, right? I like to talk about embeddings as something kind of a magic, right? You don't quite reason about magic, right? You're not supposed to just, work somewhere. The same things applies to embedding. If you think about our traditional manually created vectors like colors, for example, we know the color vector has a three dimensions. One corresponds to reds, then to green, and blue, fantastic. And we can reason about what different dimensions mean, while in embeddings, we just don't, right? They're just, some vectors which are generated by AI model, and we don't quite really have, there is no specific meaning for any of those dimensions, right? Also, they are very specific to AI model, and there is no really right answer, right? Depending on what model you use, how we trained, you will combine with completely different embeddings. And I think this is also interesting and somewhat challenging, right? Because that means if you are doing some model changes, you may need to sort of rebuild embeddings in your database, right, for your applications to continue working properly, right? So I think that is a very important things to understand. Okay, now if we go back to our databases and ask the questions, okay, but why do you actually need that databases? Some database technologies we had support for arrays, right, which can be stored, store vectors, right? We can use blobs to store vectors, right? Why do we need this kind of separate database technologies? Well, the problem is performing those kind of vector similarity search. If you just use a brute force and you can say, hey, I'm going to scan all the thousands of vectors of, or millions, billions of vectors with thousands of dimensions each, and compute similarity, which is going to be very, very resource intensive and slow. You can actually do that. And the traditional indexes which database uses, B3 indexes, they are not really helpful. They're not really helpful to optimize this operations, right? Instead, we need something else, right? Right, and there are a number of different specialized index structures, like KD streets, LHS, ANOI, right, and also NS. The W, which stands for hierarchical navigatable small world, if you wonder. Now, the two things which they provide, typically their important operations are finding the nearest vectors, right, and approximate nearest vectors. And that is also like a very interesting, right, because if you think about this case, embeddings themselves, which are kind of generated, they are kind of loose, right? When we have a lot of our kind of, traditional database stuff, right? Well, 2 + 2 is equals to 4. It can't be 5, it can be 4.5. That will be all the wrong answers. In AI, things are kind of always more loose, right? There is kind of there is no right answer for embeddings, and what that also means is what we typically do not have to exactly do exact comparison, right? Because the representation itself is kind of not completely exact, and that means we can allow for approximate search, right, for most applications, right? And that is what those systems typically provide, right? They do not provide us exact closest vectors, but they give us approximately closest vectors, which is typically good enough for most applications, right? And as you configure those data structures and choose what algorithms to use for you, you can kind of take a trade-off between how approximate is good enough for you versus how slow you want to be, right, and how much space you want to index this towards. Let's look at some example how this can be used. Well, in this case, we are looking at the GitHub issues, and you can search, do like a plain full text search for GitHub issues, right, which will work just fine, but you would often find in this case what when we look at the issues, it's not very good enough, right? Because developers often use different language to describe similar things, right? What we built here with the Manticore is the process, right, which uses a vector search to index their GitHub issues, in this case for Manticore project. And we can see what if we are going to search for memory leak, we are going to find not just all the issues which compare memory and leak, because people may not describe it as a memory leak, right? But also about some other stuff, right? Like there's somebody is talking about resolve huge RAM segments, right, or stuff like that. There is no memory, no leak, but it talks about something similar, right? And so that's is quite usable. And and this is the project, right, which is kind of a demo we created at Manticore Search, right? So you guys can either use this project for your GitHub issues you want to experiment it, right? And it's 100% open source project on itself, available on GitHub to play for you. Okay, let's talk about what machine learning tasks can be useful with the vectors, and that's actually a lot, right? You clustering, classification. You can see people doing image recognitions, right, or something like. There is a lot of different use cases. If you also have seen the modern approach, how to kind of optimize some of the enterprise processes, right? A lot of that done with RAG, retrieval augmented generation, kind of, and you can blend sort of a ChatGPT smarts with your enterprise data. All of those tend to involve their vector search technology. Now, if you want to look at some specific, I think it's never better database to look than Postgres, which has been fantastically popular with developers, and is also getting increasingly good support for vector search, because there are so many developers working about it. In Postgres, there are kind of 3 levels of vector search support. On one side, there is a PG vector, which is extension to enable kind of core vector search functionality, right? It doesn't know about models, embeddings, say, hey, you know what, get the vector in a database, I will, provide you something. Then there is another extensions kind of set of procedures called PG vectorize, which allow interfacing with various open source and SaaS, like OpenAI models, which you can use to generate embeddings, right, and have some other use of their API. And then also there is something which is called Postgres ML, which is a platform which is based on a platform to build AI apps. And they are specifically focused on this RAG, retrieval augmented generation kind of apps, which I see a lot of value built. Now, here is a quick demo about how vector search in Postgres works, right? We can see we can create a table, which we can say will have some text, for example, in our cases, and we will, create a, vector, let's say, of some corresponding image. Let's say we want to store some information, right, about their images in the database, right? We're using vector. 4 is dimensionality. As I mentioned, again, you are using typically a lot more than 4, right? You use typically much higher dimensionality, but you're using that for a demo. And we can see inserted in this database, let's say, some sort of embeddings, right? Those 2 vectors we assume have been generated from a picture displaying yellow bag and white bag. Right now, we are going to go ahead and say we have another image which has another kind of bag, right? And we going to look as there as a distance between those vectors, right? And then you can see what wherever that image using this embedding generation model looks much more close to yellow bag, right? You can see its distance is 10 times shorter than their white bag. Now, if you talk about full text search specifically, it's not all good, right? There are some disadvantages of the search based on known nearest neighbor, right? In a vector search is one. It needs a lot of processing power. It's kind of resource heavy. It's often it can be hard to explain, right? Compared to your kind of normal full text search algorithm, right? And also, as we said, it's there is no exact matches, right? It's kind of very hard to in this case to say, hey, I want only text which match exactly this sentence. So in this case, what has been created in this regard is you are using some sort of hybrid solutions. Again, there are a number of them, right? And I think that's where a lot of research is ongoing, right? And here is an interesting comparison where we are looking at results for kind of benchmark, right, for quality of research, right? Remember, that's kind of not performance, but quality for Vespa's BM25, which is kind of like a classical ranking mechanism, the Colbert, which is the AI-based or the vector KNN-based algorithm, right? And then also the hybrid, right? And what we can see is while quality of the AI itself, like Colbert, is mixed, it's actually combining both kind of classical and AI, the relevance matching can really do very well in a text search. And again, I think the more you go to the cases where people are not explaining the same stuff in the same words, the more AI powered search can be helpful. Now, if you're looking for some more examples to play with, we have also created this simple image search demo on based in this case on the Manticore engine, right, which is a full text search the solution, which also has the AI support, right? And again, that's a little open source demo where we're using Microsoft tiny clip model to generate embeddings for images, right? And you can play with it, right, or use as a a foundation if you're looking to build some apps similar to this. Now let's talk about what's next in a databases. Well, a lot of focus right now goes in pushing the functionality forward, right? I mean, if you look at this case, databases got, hey, we can handle this thing, which is absolutely essential, fast vector search, because if you don't have that, well, you can just use a database, right? You cannot store the data in database and kind of use some external indexes, right? That's, well, maybe you can, but that's kind of just, very not a very good idea, right? Now what we're seeing is a database going kind of up the stack and helping make developers easier and more productive, taking more functions. So you can see a lot of databases such as Elastic, OpenSearch, TypeSense starting to enable automatic embeddings, embedding generations, right? They typically can use those libraries, right, which are available out there, and in many cases also interface with external AI libraries, right, if you want. So I think that is something what is the next stage, we need to make their application developed even faster. Now, if you look at specifically the open source search database, right? I think that highlights the kind of a move up the level, right? We are looking at the databases to move beyond just, like a storage to really intelligence, right? Having a database to really understand what the data means and really help to create AI-powered insights to have better search possibilities. We are also looking at simplified operations, and there is also a lot of work going on how to make database just to provide us their real-time insights. Okay, to finish this up, we can see what the vector search is really their revolutionizing data retrieval, right? And this, I think, goes together with this very big change which is going on in our industry thanks to AI, and especially generative AI. We really see this emergence of their vector search database. I think it's kind of very interesting how it goes, right? Because on one extent, we have a pretty much every traditional database getting some AI, not AI, vector search functionality. And then also we are getting the databases which are specifically focused on vector search functionality, right? And we probably would see both of them exist at the same time. There is a lot of research going on into the indexes, how to improve speed and accuracy, and indexes and algorithm, right? Probably would be a better word, right? And I think this is interesting, right? Because again, this is a relatively new area, or at least in terms of kind of this massive investment, right? Unlike the databases where, solutions like a B-trees or, hash tables, bitmap indexes have been invented many, many decades ago, right? And I expect some more innovation in this space because as we will see billions of dollars a year spent on doing, this kind of vector search operations, solving that problem, making it, twice as efficient or 10 times as efficient as it is right now, right, can be, massively, massively helpful. So yeah, that is, I think, is important. And I would say if you are building any kind of search applications, all right, I think considering wherever vector search can help your users, I would, really think about, if you really think about that, because there are many things that allows to do kind of automatically versus a lot of configuration and kind of manual tuning, right? There's a lot of big search engines have been done before, right? Supporting morphology, right? And and whatever, right? I mean, again, if great models or they just can understand the meaning almost like magic. Well, with that's all I have. And if you have any questions, feel free to drop me a note. Thank you. That's all I have.